or the Q network, adaptive distillation of neural networks in deep reinforcement learning. In this paper that got accepted at the Reinforcement Learning Conference, we investigated how to distill neural networks to reduce the memory footprint of reinforcement learning agents. Indeed, memory footprint hinders RL deployment. If you have an embedded system, you really have to pay attention to the memory footprint, otherwise you will run out of memory very quickly. You also have the limitation when you have large language models and you want to deploy them, because the bigger they are, the more costly they will be. For that, sparse training seems to be the right tool to use. Indeed, you look at your weights matrix and you simply come up with a mask that is a binary mask that masks out weights and then you try to train with the masked weights. If that works, you can simply use those weights for inference. Well, then the question is how to get this mask. One promising approach is to start with a dense network and to sparsify this network during the training. Well, the only problem with this approach is that you need to decide before the training starts which sparsity level you would like to have at the end of the training. And this is very hard to know. In this paper that we call O the Q network, we develop an algorithm that discovers the sparsity schedule and therefore discovers the final sparsity level. For that, we start with a dense network and we consider several copies of this network pruned in a different manner. And we take the one that minimizes the loss to continue the training. And we continue the training by copying this network several times with different sparsity levels. And we take the one that minimizes the loss. And we do that until the training stops. This means that O the QN discovers the final sparsity level and the sparsity schedule as well. Let's look at the results. We evaluated our approach on 3 different settings. So we took 6 different environments, Mujoko environments. We first evaluated a dense approach, soft actor critic, on a small network, a medium network, and a large network. And you see that the performances are always going up here with respect to the amount of environment interactions. And here you see the sparsity schedule, so it's always 0, which means that we remove nothing. I will show here the final sparsity level of each agent with respect to the environment. We also evaluated the state of the art that we call polyprune SAC because it follows a polynomial sparsity schedule that is hard-coded to reach a sparsity level of 95%. You can see that for large network and medium network, things are going very well because the performances are the same as the dense network. However, for the small network, things are going pretty bad. And that's because the sparsity level is too optimistic. As I said before, it's hard to know in advance which sparsity level to enforce during training. And it's very frustrating because in the middle of the training, you see that the performances were going down and we kept pruning the network. In contrast, our algorithm that we called O de SAC reaches similar performances than the dense approach without any supervision in terms of sparsity schedule. The sparsity schedule has been discovered by the algorithm. If we give a larger network as input to our algorithm, the sparsity level increases. And this makes sense because with more parameters, you can sparsify more the network. You can see here the final sparsity levels are actually higher for the medium network. And this happens the same if you further increase the network size. Interestingly, the sparsity levels are different for every environment. And that's because why would the sparsity level would be the same for different environments? Thank you for listening. I hope I convinced you that our algorithm, or the Q network, discovers the sparsity schedule, and it's discovered at the agent's learning pace because we're looking at the loss. You can see here a link to the code, to the paper, and this is a link to a related work that we developed around hyperparameter optimization. Thank you.